In this video, I'm going to talk about how sound waves interfere constructively and destructively with each other. And I'm going to do a derivation of interference from two sound sources. The derivation is a little bit complicated, but I think it's good for you to see because it's going to come in handy again in Physics 7, where you'll see the same derivation done for interference of light waves in a famous experiment called the double slit experiment. First, let's talk about interference in general. Let's say we have a loudspeaker that's creating some sound, and we feed that sound through two separate pipes. And here's our listener, listening with their big ears. So the sound will travel in one of two, no, it'll travel in two paths. Not one of two, but it'll travel in two paths. These two paths may or may not have the same length. We'll call one length R2 and the other length R1. Now, if the lengths differ by a full wavelength, then the sound will constructively interfere with itself. The sound waves will be in phase by the time they reach the listener. So if the difference in lengths is an integer number of wavelengths, then you have constructive interference. On the other hand, if the difference in these lengths is half of a wavelength, or an integer plus 1/2, then you have destructive interference. The way to think about that is constructive is what happens when you have two sound waves that overlap. And destructive is when you have two sound waves that go in opposite directions. They'll destroy one another. All right, so I want to keep these relationships in mind. I'm going to erase all this now to create room for the derivation I want to do. Let's say we have two loudspeakers and they are separated separated by a distance d, and there are distance L, a perpendicular distance L, from some line or plane where our observer or listener is going to be. Let's put our listener here. With their big listening ears. At a point P, that is a distance Y above that middle line. So there is some distance, R1, from the first speaker to our listener. There's a distance, R2. Sorry, that line wasn't very straight. It's a terrible straight line. You get the idea. R2 from the second speaker to the listener. And if you draw a right triangle here, this distance, we'll call it delta. That's a Greek letter delta. Is R2 minus R1. That's the difference in these two distances to the listener. And as we just discussed, if this distance is an integer number of wavelengths, the listener receives constructive interference. The listener hears a loud sound. If this distance is a half integer number of wavelengths, the listener experiences destructive interference and gets a very quiet sound. So let's do some geometry to figure out how this path length difference depends on the listener's position. Because you can imagine that if the listener's right in the middle, they're going to experience constructive interference. But as they move away from the midpoint, they'll experience some regions where this path length difference will be half integer and they get a quiet sound, and then it'll go back to being integer and they'll get a loud sound. And it keeps alternating as they move farther away from that midpoint. Same thing would happen if they moved in this direction. All right, so let's look at my geometry here. Draw another line and define this angle theta. By geometry, it's the same as this angle theta. And this theta is related to, it's part of a right triangle where one leg of the right triangle is L and one leg of the right triangle is Y. So opposite is Y, adjacent is L, opposite over adjacent is tangent. And now there's this small angle approximation that we talked about when we studied pendulums. When this angle is small, we can use a similar kind of small angle approximation and say that this is approximately sine theta. Tangent is roughly equal to sine for small angles. So we have sine theta equals y over L. And we also have sine theta in this right triangle. D is the, you see this right triangle? D is the hypotenuse, delta is the opposite, and there's our theta. So we have delta equals D sine theta, or delta equals D times Y over L, but this delta was our R2 minus R1, our path length difference. And now we can use the relationship we had earlier, which is that when this path length difference is an integer, we have constructive. So dy over L is n lambda for constructive and destructive. Dy over L equals n plus 1/2. So that was a whole lot of geometry, and I realize it's kind of hard to see, so I encourage you to take a look at your textbook. And I think in chapter 24, they do this derivation. Let me draw a different sketch that just shows what the waves are doing. Okay, if this is the scenario, you would have constructive interference where the listener is located. Because these waves end up with their peaks and troughs lined up in the same place by the time they reach the listener. So that's constructive. On the other hand, let's see if I can get this drawing right. If they're lined up a different way. Try that again. This isn't easy to draw. Okay, what I tried to show, I missed. Okay, third try. Better. Okay, what I tried to show this time is that by the time both waves reach the source, they are 180 degrees out of phase. This one's going up and that's going down, that's going up and this is going down, and so on. And so at this point, the listener will experience destructive interference. All right, so let's do one quick example from the textbook. Example 14.6. Example 14.6 is this scenario, and they just give you some numbers for it. They say that the distance from the speakers to this plane is 8 meters. The distance D between the speakers is 3 meters. The distance from the observer to the center point is 0.35. And they ask, where do you find the first location of destructive interference? What's the first minimum in the sound level? Where's that located? So for destructive interference, the path length difference is given by this, and the first location will be where n equals 0. So lambda over 2 is your path length difference. And with all this fancy geometry, we derived that this path length difference is dy over L, and we can solve that for lambda. Putting in the numbers, you get 0.2625 meters. And the frequency of sound that must be playing then is V over lambda, or 1306 hertz. That's where we're assuming V is 343 meters per second in room temperature. So if these two speakers are playing this frequency, that will produce a first minimum, a first location of destructive interference at this point right here, 0.35 meters away from the center.